Hello, this is Mrs. Nearing, and we're going to be talking through some stoichiometry notes here, talking about gravimetric analysis, percent yield, and some stoichiometry involving gases. So, looking at the AP exam, there are two main experimental techniques to be thinking about here in Unit 3, and you can see these are the learning objectives here from the College Board, and those two experimental techniques are one is gravimetric analysis, which is weighing stuff, and then the other one is titration. So you can see there's two objectives here related to titration and one related to gravimetric analysis. So gravimetric analysis is one we have not done yet, and a description of gravimetric analysis is you have two substances mixed together. It might be two solutions mixed together, like in a precipitation reaction, and then you're going to form a solid in this reaction, and then we're going to collect that solid and purify it and weigh it, and then we're going to use the mass data to do some stoichiometry to determine the concentration of the original reactant. So that gravimetric, think gravity, has to do with like weighing things with the weight of something. So you're going to make a solid and weigh it. Here's an example of a gravimetric analysis problem. Notice this is a double displacement reaction. It is a precipitation reaction in which your two solutions combine and form a solid. And you can imagine this type of reaction. We would mix together two aqueous solutions. You'd form a solid, and then you want to separate out that solid. And you might do that by filtering the solid. That's a common way of doing it. And then drying it to make sure you get the mass of your pure dry solid sample. So let's work through an example of this. So we mix together a 50 ml solution of copper chloride with unknown concentration, and we're going to mix it with excess of sodium phosphate. So we're going to assume our sodium phosphate solution is really concentrated. There's tons of it, and we're going to have excess sodium phosphate left over at the end. So that means we're going to assume all of our copper chloride gets reacted in this reaction. So we do this reaction, we collect and dry and weigh the solid precipitate and find that we have made 18 grams of this precipitate, which is copper phosphate. And you're trying to determine the molarity of the copper chloride solution. So first step in any type of stoichiometry problem should always be find moles. So I'm going to take this mass value and I'm going to convert it into moles. So I'm going to go from grams copper phosphate to moles of copper phosphate. And whenever I'm converting from grams to mole, I should be using the periodic table and looking at my molar mass. So if I look on the periodic table and I add up all the molar masses, I'll find that 1 mole of copper phosphate weighs 380.4 grams. It's a big compound. It's got a lot of stuff in it. Okay, so that gives me moles copper phosphate. I'm trying to find molarity of copper chloride. So I've got to convert from copper phosphate to copper chloride. And that's where my balanced chemical equation comes in handy. I'm going to use my mole ratio. So 1 copper phosphate, in order to make that 1 copper phosphate, I need 3 copper chlorides. So first step, find mole. Second step, use your mole ratio. Now, I should fill in the word mole. Okay, so if I stop and solve for here, grams cancels out, moles copper phosphate cancels out. I'm going to have an answer that is in moles copper chloride. And if I plug that in my calculator, I should get 0.142 moles of copper chloride. The question asked me for molarity. So molarity is moles per liter, and my moles is 0.142. My volume is 50 milliliters, so I'm going to divide that by 1,000, and I will get 0.0500 liters. Remember, those last two zeros are still significant, and when you plug that in, you get 2.84 molar is my molarity. Okay. So that's just what gravimetric analysis is in general. Now let's talk about the idea of percent yield. And this is taken from your textbook. They talk about this in Chapter 4, Section 3. And there's some defining terms here. So the limiting reactant, there's a limiting reactant and excess reactant. We'll talk about how to determine what those are in the next lesson. But for now, just be aware, limiting reactant is a reactant that's completely used up. The other reactant we call the excess reactant. We assume there's a bunch of it around. We basically don't have to worry about how much excess reactant there is. There's a ton of it. There's some there at the beginning, there's some there left over at the end. So the limiting reactant is the one that determines how much product we will make. The theoretical yield is the amount of product that can be made based on your limiting reactant. So basically what this means is your theoretical yield, this is the number that you would calculate. You're going to do some stoichiometry and you're going to calculate, oh, this is how much product I should make in theory. Then we actually go and do the reaction in a lab. You actually do the reaction, collect the precipitate, dry it, weigh it, and that will be your actual yield, is what you actually collect in the laboratory. And reactions aren't perfect. Your actual yield is usually not the same as your theoretical yield. And so we will then calculate what we call the percent yield, which is what you actually got divided by what you theoretically should have gotten. And, ideally, if it's a perfect reaction, your percent yield's 100%, but a lot of times it's much lower than that. So let's look at a sample problem to figure out the percent yield of this reaction. So this is a reaction involving aluminum and chlorine gas. This is a combination reaction. And we find that 2 grams of chlorine react with an excess of aluminum, and you make aluminum chloride, and then we measured and weighed how much aluminum chloride we actually made, and we should be able to find the percent yield of this reaction. So your first step is you have to figure out what your theoretical yield would be in this reaction. So your theoretical yield is based upon, it's a calculation based upon your limiting reactant. It's the reactant that gets all used up. So this reaction tells us that chlorine gas is our limiting reactant. How do I know that? Because it says that aluminum is in excess. So that means that my chlorine gas is the one that's determining how much product we make. So I have 2 grams of chlorine. First step, whenever you're doing a stoic problem, is find moles. So I'm going to convert grams of chlorine into moles of chlorine. And whenever I'm going from moles to grams or vice versa, I'm going to look at the periodic table, and that tells me 1 mole of chlorine weighs, let's see if we add that up, I believe it's 70.9 grams. Next step is, so I know moles of chlorine, I'm trying to find aluminum chloride. I should have circled this whole thing there. Okay, and so the equation tells us that for every 3 chlorines, I will make 2 moles of aluminum chloride. And then I want to figure out how many grams that would be. So I'm going to go from moles aluminum chloride to grams aluminum chloride. I should throw in a mole here. Mole. Okay. And again, I'm going to look at the periodic table, and the periodic table tells me that 1 mole of aluminum chloride is 133.3 grams. So if I stop and plug this in my calculator, I will get 2.51 grams of aluminum chloride. That is how much I should make in theory if everything goes perfectly and all my chlorine gas gets used up. When I actually perform this reaction and collect solid, I find that my actual yield is 2.25 grams. So your percent yield is going to be what you actually got divided by what you should have gotten in theory, and then you multiply it by 100 to turn it into a percentage. So that's 2.25 divided by 2.51 times 100%, and you end up with an 89.6% yield, which is actually pretty good percent yield for a reaction.